No, sir.
Okay. The other thing is that if you put n equals to 0, right, then we see that our wave function psi of 0 is 0, right? And why is that? Because we see that cosine of minus n yeah, so let's see, okay. Yeah, exactly, right? Because when n is odd, right, that's when we have, when n is even, that's when we have sine, right? So psi of 5 of x is going to, sorry, psi of, okay, psi of 0 will be a tilde times sine of n 0 times pi over Lx, right, which is 0. Okay, so we see that the 0 wave function, does not represent a physical state. Okay. Because it doesn't have any probability or blah blah. It's a trivial solution to the Schrodinger equation. Okay. So that means that we can take n to be greater than 0 and an integer. So an integer, okay? And okay, let's call it, and a natural number. So is 0 included in the natural numbers? Does anyone know? In the definition? Anyway, you know what I mean, so that's all I care about, yeah. So, okay, so what are the solutions? The solutions are psi of n is equal to, well, it's a function of x, so let me do that properly. Psi of n of x is equal to 2 over L square root sine of n pi over L of x for n equal to say 1, 3, 5, dot, dot. Is it? No, I think it's the other way around, right? Yes, it's when n is actually 2, 4, 6, right? Yeah. And on the other hand, cosine 2 over L, and there is cosine of n of pi over L of x. And here n is going to be 1, 3, 5, dot, dot, dot. Okay? So what are the energies? So if you want the energy, we have to look at the value of k. So k can only take these values here. KL is equals to n pi over L, right? So let's go back. So KL is n pi. So K is 2e by h bar square root of 2e. Now there's a 2m, right? 2me. Yeah. So K is 2me by h bar, there's a square root, times L is n of pi So if I square both sides, I get, so let's call this En. 2m En is equal to n squared pi squared h bar squared divided by L squared. So E of n is n squared pi squared h squared divided by, say, 2 m L squared. Okay, so this is my energy. Eigenvalues of, for n equals to 1, 2, 3, 4, dot, dot. Okay, any questions? This is the energy levels allowed in a particle in a box. It is proportional to, so if you recall, the hydrogen atom, E of n, was proportional to, what was the n dependence there? Do you remember?
-1 over n squared, I think.
Very good. Yeah. Yeah. And so it's a different kind of, particle in a box. Here, even if you go to n equals to infinity, you don't really get to a unbounded state. Whereas here, if you go to n goes to infinity, E goes to 0, and before that E is minus. So, and that's basically the limit beyond which the electron becomes liberated from the tyranny of the nucleus, right? And it becomes a free particle. Okay? So for the hydrogen atom, we have some energy limit, and it just goes and there is a limit. There are an infinite number of energy levels, but there's a limit to it. And beyond that limit, what we have is that we actually have a particle that is free, that is moving with positive kinetic energy in a potential, generated by a Coulombic force. Okay. Okay. All right. So now let's look at the wave function more closely. Okay. Let's make some comments. And the comments are that the basis wave function that we have found is that, the wave functions have definite parity, right? So for example, they're even and odd wave functions, right? And they have the cosine wave functions, they're even wave functions, the sine wave functions, they're odd wave functions, right? The other thing is to note is that energy is quantized. And this has to do with the fact that we are working with a bounded system. Okay, we are working with bound states, or I think it's not bounded, it's bound system, right? Yeah. So this is a consequence, and we'll get to the more general theory of why that is so in the next lecture. Okay. So sorry about that. This is a consequence of a bound system. Okay, so this has to be, this has to do with the boundary condition, and for the wave functions not to go to infinity at not to diverge at infinity, and also the fact that these wave functions have to smoothly join in. I can actually kind of tell you why, right? So let me just say why. So if I look at the if I look at the solution, it seems superficially that we have two independent constants A and B, but that is actually not the case because of the overall normalization. Only the relative value of A and B matter. Okay, and when you go far away to plus infinity and minus infinity, well, in this case, you don't have to go to infinity. What happens is that you have a finite value of x, this wave function has to go to 0. And that is something can only be satisfied if, if this wave function has a minima at the boundaries, right? So, but it can only have minima at the boundaries for specific values of k, right? And that's why it's quantized. But so I think, it's not the best idea to get an intuition about why energy levels of bound system are quantized from the particle in a box, because in a sense, the particle in a box is a very artificial system where the wave function is forced to go to 0 at the boundary between different regions. So later we'll come to more realistic systems where the boundaries are, where the potential is not infinitely high, okay? So, all right, let's look at some of the, let's make some more comments. Let's look at the ground state, okay? So the ground state energy happens when n equals to 1 and E 0. For some strange reason, ground state is always denoted by a naught with the energy, although it corresponds to n equals to 1. The ground state is given by h bar squared, pi squared over 2m L squared, okay? So if I told you, consider a potential, whose width is L, which is infinitely deep, right? And and the particle mass is m. You could have pretty much guessed the ground state up to an order 1 constant, right? Could you do that? So if I give you, somebody's going to say something, L, if I give you M, if I give you H, there's only one combination of these constants which are going to give you something which has the dimension of energy, right? So the only way that you can combine these things, the simplest way you can combine these things to give you energy is going to be, H squared over ml squared. Okay? So this is the power of dimensional analysis. So, pi squared is, what is pi squared? It's about 10, right? Or between 9 and 10 or 11, I don't know. So this is very, so up to some order 1 constant, you could guess what the energy level, what the ground state energy was, right? So this is known as dimensional analysis, okay? This is the physicist's best friend. Okay, what do these wave functions look like? Remember that the ground state wave function is going to be n equals to 1. So is it going to be a sine wave or a cosine wave?
Cosine, I guess, because n is odd.
Exactly. So, and it must be of this form, right? It must go to 0 exactly at the boundaries, right? Okay. And what about n equals to 2? What do you think? Is it going to be a sine wave or a cosine wave?
The next one should be sine wave.
Very good. So it'll be something like this. Sorry. It's not, yeah, okay. What about n equals to 3? It's going to be a cosine wave, right? And you can check that this is essentially going to be just this thing. Okay, so on and so forth. So what we see is that the nth energy level, the nth energy level has essentially, n minus 1 nodes, disregarding the zeros at the boundary, right? And this is going to be a generic feature of one-dimensional systems, okay? So the ground state will have no nodes whatsoever, right? And the first excited state will have one node, and that node being this point. And the next excited state is going to have, I didn't draw it right. So let me draw it right. So this is the good thing about having a heuristics, right? So we can actually correct ourselves. So it's going to be, oh dear, what happened to my drawing today? Okay, so this is going to have one node here, another node here, two nodes, right? Okay, and so on and so forth. So, and this is a feature which is going to be preserved for all one-dimensional bound states, okay? Okay, so this is a generic feature of all one-dimensional bound states. Okay. Do you have any questions?
No, sir.
So the potential, one-dimensional particle in a box is a very useful problem to have, to know about. Okay. So